Good morning, doctor. We are group 5, and today we are going to present the task 2, which is called Taming the Spark, and it is related to the conductor emissions and EMI filtering. In this video, our group will illustrate how noisy electrical components, specifically the arcing process of a DC motor, pollute a power supply with broadband conductor electromagnetic interference. To fix this, we'll walk you through the design of a custom low-pass filter using passive components, and then prove its effectiveness by comparing the before filter and after filter voltage waveforms using multi-sim transient simulations. To design an effective filter, we must first understand the electromagnetic field theory behind the noise. EMI travels in two main ways, differential mode and common mode. And now I explain to you about the common mode noise. Common mode noise currents flow through both the signal and return lines in the exact same direction with equal magnetic and phase. According to Ampere's law, these currents induce magnetic fields, but because they flow in the same directions, the magnetic fields don't cancel each other out, they superimpose. This constructive interference creates a strong unified magnetic field around the cables, effectively turning them into a transmitting antenna that causes unwanted radiated emissions. In real-world circuits, this is often triggered by ground loops from ground potential differences or ungrounded sources. To solve this, we can implement proper grounding practices, use shorter or shielded cables to block external EMI, and place ferrite beads around the cables. Most importantly, we can install common mode chokes on the power lines to block these specific emissions.
So for differential mode noise, it's the normal operation current that flows through the signal and return line, carrying the useful signal and information. Current in both lines have same magnitude but flow in opposite direction with 180 degree phase shift. Differential mode noise is also referred to as normal mode noise because it originates from the normal operation of the circuit. Differential mode noise current is the noise current that arises due to the normal circuit operation. It flows in same direction as the power supply, and this noise current does not get the ground path. There are some causes for differential mode noise, which include noise on power line, noise source present either at the power supply side or within the lock, variable speed drive control, and harmony of digital logic circuits.
Hi, I'm Roland. I will explain how capacitors help to reduce electrical noise in a circuit. Capacitors reduce electrical noise in three main ways. Across the line, capacitors remove line-to-line and line-to-ground noises. Bypass capacitors remove noise from DC power sources. Decoupling capacitors reduce size of loops within circuits, blocking external noise. The basic role of a capacitor is to store energy in an electric field. It can quickly supply transient current during sudden changes. For a constant voltage, no current can flow through capacitor, but when the voltage changes, current can flow through it. Capacitors are used for noise reduction because they provide a low impedance path for high-frequency noise. High-frequency noise is diverted to ground instead of reaching sensitive circuits. It also helps stabilize the power supply voltage during sudden load current changes by supplying transient current from stored energy. Three important rules for noise suppression are: use a capacitor with low impedance at the noise frequency, place it close to the lock, and minimize PCB trace inductance.
Hello everyone, my name is Kayong and welcome to our demonstration. First, this is the physical circuit before the EMI filter is added, which we simulated it in multi-sim. This V1 represents the 5V DC source. This is the main power supply, establishing a baseline 5V DC voltage for the circuit. And R1 is the series resistor that models the internal resistance of the battery. L1 is the pulse current source, which functions as a primary noise generator. And R2 and L1s are connected in series, and together they models the characteristic of the motor, which R2 represents the internal resistance of the motor coils, while L1 represents the motor natural inductance. And the oscilloscope is connected to observe the voltage on the power line. Looking at the waveform, we can see that the output is not perfectly smooth. Although the average voltage remains close to 5 volts, there are repeated sharp voltage spike and high-frequency oscillations. This spike represents the conductor electromagnetic interference, or EMI, traveling through the power line. Next, we added an LC low-pass filter between the noise source and the load. Same goes here, we simulated it in the multi-sim. The filter consists of a series inductor and a capacitor connecting to a ground. The inductor provides high impedance to high-frequency noise, making it difficult for the noise to pass through, while the capacitor provides a low impedance path to the ground, diverting the unwanted high-frequency components away from the load. Let's look at the result. The blue trace represents the voltage directly at the noisy source, where those half spikes are still happening, and look at the red trace, which represents the voltage at the main power supply. It's a completely flat and stable line. The inductor successfully blocked the high-frequency current, and the capacitor diverted the remaining voltage ripples to ground, ensuring our main power source is completely protected. Since this part of project focus on simulations, the reduction in EMI is verified by comparing the oscilloscope waveform before and after the filter. The decrease in the voltage spike represents a reduction in conductor noise, which proves that our filter is working successfully.